Hey y'all, today instead of giving new content or reinforcing kind of the distance and the velocity ideas that we explored during class, I really wanted to take a second to kind of give a little help with the homework, some of the questions that I feel might be a little conceptually difficult, that have a lot of vocab in there that we're just starting to get familiar with or we're trying to familiarize ourselves with again. So going over two questions, hopefully this video will clarify some concepts that we were going over during the overall review, and that you can be a little more confident going into future problems having to deal with these. So our first question has to do with continuity. So remember, continuous means that we have a function that's nice and smooth. There's no jumps, no skips. If we have a continuous function, it's basically saying that we can hold down our pens and follow the line with the function without ever lifting up our pens. So we are going to be looking for a value a in this piecewise function. We're going to find the value of a that makes the whole entire piecewise function continuous. Or if we're following our first function up to 2, and we continue to this next function after 2, we'll never have to lift up our pen. And so this usually isn't the case when we look at piecewise functions. So for example, we might have a piecewise function that's broken apart at x equals 3. And we might have one function that looks like an upside down parabola up to 3, and then it might jump up to a regular line right at x equals 3. So notice right here, if we try to trace over this, we're actually going to have to jump up. We're going to have to make the pen leave the paper in order to continue with our function. So this is an example of a discontinuous function. So what we want to do is make sure that right at this border, our first function gives us the same exact output as our second function. So to visualize our h of x, I'm going to kind of follow a similar pattern. I'm going to make our first value blue. It's going to be a blue line. And then our second value, we're just going to continue using the green. So if we're trying to visualize this thing, well, we know that this guy is going to look like, so 1, 2, 3, 4. So first off, we need to establish our borders. We know that 2 is going to be the border. So x equals 2 is our border between functions. And we know to the left of it, we're going to be taking on this part of our h of x. For x values less than 2, it's going to follow the square root format. So just remembering our shifts and graphs and all that fun stuff, we know that our square root function kind of looks like this, but we have to shift it to the left 2 units and down 1 unit. So to the left 2 units, down 1 unit. And so our first function is going to look a little bit like so our first function is going to look a little bit like this. It's just a sketch. And then right up to 2, it's going to look like this. So what we want to do is figure out what a value we have to put in here so that when we look at a parabola, we actually get something that looks like this. Okay, so we want our parabola to kind of, so we know it's a parabola because of the square. We want it to cross right there. We want to find the value of a that makes it hit our x equals 2 value at the same spot as our first function. And so just to show you, to clarify what I mean, we could choose different values of a, and it's going to change the way this right side looks. If we make our a bigger, we might get something that looks like this, which isn't going to be very helpful because we get that discontinuous jump. It could also look something like this if we make our a really big, which notice that discontinuous jump also happens. So we want to hit that sweet spot for a. So our goal here is to figure out, well, what does our first function output for x equals 2? And then we can set this guy equal to that at x equals 2 in order to figure out what value of a will give us that nice, smooth, continuous look. So let's start off with h of x, the left side. So for x less than x equal to 2, our first function is going to take on the value of 2, the square root of 2 plus 2 minus 1, or the square root of 4 minus 1, which just comes out to 1. So we know that when x equals 2, our y value is going to equal 1. So we want to do the same exact thing over here. We know that this function right here, when it's evaluated at 2, has to come out to a 1, so we get that nice continuous function. So let's do that for the other side now. So at x equals 2, we know that this guy will simplify down to a times 3 plus 1 squared. So let's just deal, or 2 plus 1 squared. So we're replacing the x with the 2. So we know that this is just going to be a times 3 squared, or a times 9. So at x equals 2, we know the right side comes out to 9a. But we know that the 9a, if it's continuous, should come out to a y value equal to 1 right here for both sides. So we can take this whole thing, set it equal to the 1. And so we can divide both sides by 9 and actually find out that this a should equal 1 over 9. And we can actually check this. We can check both sides at 2, and if at the border you have the same exact output, hopefully y equals 1 for both sides, that we actually have this continuous function. So we actually checked it here, but no harm in checking it again. So at x equals 2 for our blue side, for less than 2 going up to 2, we have the square root of 2 plus 2 minus 1, which we showed up here, actually gave us a value of 1. So now let's try to do it with the right side, except we're going to plug in our value for a. So we know our a is 1 over 9. We know we're looking at x equals 2, so 2 plus 1, and then we're squaring the whole thing. So hopefully this comes out to an output of 1 as well. So we have 1 over 9 times 3 squared, which is just 1 over 9 times 9. What do you know? We also get an output at 1 for both of these functions at x equals 2. So if we're looking at this graph, we'd actually have that nice, smooth, continuous function over this line, which we've shown can most of the time be discontinuous. All right, so that's the first question. The second question we're going to go over is 1-142, question 142, which has to deal with holes in asymptotes. So we're going to use algebra to identify each of these holes in asymptotes. And this is really going to just be a lot of review on just factoring, getting these different values down, or getting these different techniques down. So for each function, use algebra to identify all holes and asymptotes. Okay, so we're going to start off with our first one. This one's really just going to be a technique related one. And we're also going to just have to discuss x squared plus 4x minus 21. We're also just going to have to discuss constitutes a hole, what constitutes a asymptote. And remember, if we're looking at, just a review up here, a hole is just a certain point where your function, where a specific input doesn't have an output. And then we know that an asymptote is a value that our function approaches but never quite hits. So this is going to be our asymptote. So let's check this one out. We have a fancy function. We know that if we have a quadratic in the bottom and a factor up top, our best bet is probably going to be to factor to simplify the quadratic, turn it from standard form to factored form. So remember, we have to collect our a, b, and c. So we have a equals 1, b equals 4, c equals negative 21. We get our crisscross going. We know that we want to multiply, we want to multiply up to our c, or in other words, find two values that multiply up to negative 21 and add up to 4. So when I'm thinking about this, I might choose 7 and negative 3, or I will choose 7 and negative 3. So just by just doing enough of these, you can start to find that pattern and see that pattern pretty easily. I like to think of it as like a more straightforward Sudoku or something. You're finding these patterns to match very specific conditions. So just as a general check, 7 times negative 3, that does give us negative 21. 7 plus negative 3, that'll give us a 4. So we've solved our pattern. So this means that we're going to have our quadratic turn into x minus 3 times x plus 7. So we can just put this right here. X plus 7, x minus 3. So here's where we can actually tell the difference between a hole and an asymptote. So if we're talking about a hole, what we're looking for, a hole comes up in the values of x where the factors cancel. So if we're taking a look at here, notice how we have an x minus 3 factor in the top and x minus 3 factor in the bottom. So here we're going to actually have a hole at x equals 3. Our asymptote happens wherever this is left over, and we can see this by just looking at the simplified version. So our asymptote, we're actually going to look at the simplified version, and notice here that when we're looking at our simplified f of x, we actually have a certain value where this thing actually becomes undefined. If we're looking at x equals negative 7, so our asymptote, values of x where the simplified function is undefined. And by undefined, I just mean that we're dividing by 0. There's no number that we can represent by 1 divided by 0. We can represent 1 divided by 0 by. So check this out. If we put in a negative 7 here, we'll find that our function actually simplifies down to 1 over 0. So we know that at x equals negative 7, we're going to have an undefined, or an asymptote. So what I would recommend doing is actually graphing this thing out on Desmos, graphing this function out on Desmos, and checking to see that you actually have a hole at x equals 3, as well as an asymptote at x equals negative 7. So our last example is, last example is a little bit more algebra. Remember, we're looking for either common factors that'll cancel for our holes, or values that when we plug it into our function, we get an undefined value for the asymptote. So in this function g of x, we have x to the 4/3 power divided by x squared minus 2x. So here, what I would do first is just try to factor out an x. So we see that we can simplify this to x times x to the 1/3 power. So 3/3 plus 1/3 will give us back to 4/3. And then here we can do x times x minus 2 times x. I'm just really expanding this out so that we can see where our certain values are. So here we can see, well, from the top we can just pull out that x, just like we did before. And then over here, down below, notice how we can pull out an x from both of these factors. And then what's left over is the values without those x values being multiplied. So we're left over with x minus 2. And so first off, we want to look for those holes. What values of x do our factors cancel? Well, here we have an x that cancels. Here we have an x that cancels. If we wanted to make it in a very similar way as here, we can see that x is actually can be represented by x minus 0 times x to the 1/3 all over x minus 0 times x minus 2. So here we can see that we'll have a hole at x equals 0. Now we got to look at the simplified version, whatever's left over. So our simplified version, g of x now, is going to be x to the 1/3 divided by x minus 2. So looking at this one, we can easily see that if we put an x value equal to 2 in here, we're going to get an undefined value for this function. So at x equals 2, we're going to have our asymptote. X equals 2. So we can verify that by plugging in 2 into our g of x. Here's our check. So g of 2 simplified is going to be 2 to the 1/3 power, whatever that is, divided by 2 minus 2, or it's some value divided by 0. So we found that we verified that asymptote. All right, so hopefully this clarified a few ideas. Once again, I would really recommend you graph these out on Desmos, verify that you get these holes here and these asymptotes right here. Noticing that if we can look at the algebra, we really don't even need to graph these things out. We can just trust our instincts, knowing that those factors that cancel are going to give us the holes, and the values of x that give us an undefined output for a function will give us the asymptotes.